I'll go through the example at the bottom of page number 2 from your handout. So I have a piecewise function graphed, and I'm asked to talk about the limit, to name the limit from the left of f of x, the limit from the right of f of x, and the actual limit of f of x, all as x approaches some different x values, so 0, 1, 2, 3, and 4. So notice here one special case at x equals 0. It doesn't make sense to talk about the left-hand limit because as I come toward x equals 0 from the left, there's not even a function over here to walk along. So we wouldn't even talk about the left-hand limit, the limit of f of x as x approaches 0 from the right. Sorry, as x approaches 0 from the left. The limit of f of x as x approaches 0 from the right, I can walk along the function coming from the right-hand direction, and I get to y equals 1. So that's the limit y equals 1. The actual function value when x is 0 is 1. That's where the colored in dot is. So again, this 1 is a special case. I can say that the limit as x approaches 0 of f of x does exist and is equal to 1. Normally I would need the left-hand limit and the right-hand limit to match. Here the left-hand limit doesn't even, you can't even talk about it. So it's not that it doesn't exist, it's just not part of the domain. So we can still say that the limit of f of x as x approaches 0 is 1. Alright, so let's erase this up. As x approaches 1, I can talk about the limit from the left. The limit of f of x as x approaches 1 from the left is that y value, which is 0. The limit as x approaches 1 from the right is this y value, which is 1. The actual function value is wherever the colored dot was. That happened to be at y equals 1. So the question, does the limit of this function as x approaches 1 exist? I would say the limit as x approaches 1 of f of x does not exist because the limit from the left-hand side, 0, does not match the limit from the right-hand side, 1. If you want to write DNE instead of do not exist, that's an accepted abbreviation. At the place where x equals 2, I could talk about the limit from the left-hand side. If I approach from the left-hand side, I'm approaching that y value, which is y equals 1. If I approach from the right-hand side, I approach that same y value, which is still y equals 1. The actual function value, the colored in dot when x equals 2, is 2. Which is different, but I can still say that the limit exists. The limit of f of x as x approached 2 from the left was equal to the limit of f of x as x approached 2 from the right. So I can say that the limit as x approaches 2 of f of x exists and it's equal to 1. Now we can explore what happens as x approaches 3. The limit as x approaches 3 from the left, looks like up there is y equals 2. The limit as x approaches 3 from the right, again, y equals 2. This time the actual function value f of 3 looks like it equals 2 as well. The colored in dot is where I sort of expected it would be. So I can say that yes, the limit of f of x as x approaches 3 exists. The limit of f of x as x approaches 3 is equal to 2. And here the case as x approaches 4 is similar to the case as x approaches 0. It doesn't even make sense to talk about approaching x equals 4 from the right, since there isn't any part of the domain of the function to the right of x equals 4. The limit as x approaches 4 from the left appears to be 1. The limit as I approach from the right doesn't make sense to talk about. The actual function value happens to be 1. And I can say that the limit as x approaches 4 of f of x is equal to 1. The left-hand limit is 1, and the right-hand limit doesn't make sense to talk about. So it's okay to not worry that it's not equal to the left-hand limit.